this an epsilon?
Which one?
That's what the letter is, right?
Yeah, well, I think it's a xi, but I call it epsilon because I think xi is something else, but my Greek alphabet is pretty poor. So I've always called it epsilon.
Yeah, it just looks like a squiggle.
I've called it squiggly in the past.
So I just write it like kind of like a little an E with a little bit too many curves in it.
Yeah, that's what I do too, honestly. I just start squiggling and then, and it ends up as a Greek letter.
It's been so long since I evaluated a double integral. That's been at least 2 years, I think.
It's definitely not a regularly practiced skill, even for most people, I'd say. Yeah, we'll do an example today.
And so once you take that x of epsilon derivative, that's when you end up with your Jacobian, right?
Exactly. Yep.
So this is that sound right when I remember that?
5 for the homework problem. Oh, okay. Yeah, it's been a while since I've looked at it.
Well, and then that problem too, the 2D one, we did that last time, right?
Yes,
Triangle with the coordinates.
exactly. Yeah.
So we're gonna have to do that thing where we do those like 16 or 9 or whatever they are, integrals or whatever. Well, they're just sums, right?
Yeah. Yeah. So they end up just being sums.
Okay.
Mhm. I guess. Is that a cat or the recording?
Yeah, it was a cat, yeah.
A real cat?
No, no, it's a recording.
Okay. I'm excited for a second.
No real cat, you know.
Stop flash right now. We're going to see the cat.
You only have one cat, Dr. Frank?
Right now I have 0 actually. My cat passed away actually.
Sorry for that.
How long did you have your cat?
Well, I've only had her since I started living with my wife, so about 3 years, but my wife had her for 18 years. Yeah, so she lived a long, very long,
Long time.
very long, good life. Yeah. It was her time.
Were you a cat person before that?
My mom never let me have pets growing up, but I do prefer cats.
Over dogs?
Yeah, the cats kind of stay out of your business then.
Yeah. More independent.
Exactly. Okay, it's 7 o'clock, so let's go ahead and get started. Good evening, everyone. How's everyone doing today? Good, right? So today we're going to be continuing on with our 2D stuff, all right? And so we're going to be starting out with Gauss Quadrature in 2D. And so that's going to help you out with one of the homework problems. And so one of the homework problems asks you to do that, and so this will help you out with that. Okay. And then we're going to move on to, I think, probably I would say the culmination of a lot of things in this class, which is isoparametric elements. Okay. And so isoparametric elements is pretty core. You know, I've been hyping this up for a long time. It's pretty core to, you know, I would say most modern finite elements. And so it's kind of a combination of, you know, of Gauss quadrature together with, you know, the methods that we've been learning on how to produce element stiffness matrices. Okay. And of course, it's a core part of your final project as well. And so, you know, we might not get to it today, but on Monday, you know, we're going to go over the isoparametric, I call it the isoparametric algorithm. And that's basically the exact one that you're going to use for your final project. Okay, and so that's it for my announcements. So are there any questions I can answer before we get started? Okay. Oh, so the study guide went out yesterday. You know, please remember to vote in the poll. And so I'm probably going to film the review video on Friday afternoon. Okay, so you can expect to get the review video by then. Okay. Okay, so let's go ahead and get started. And so let's talk about Gauss quadrature in 2D. Okay. All right. So, you know, we've seen Gauss quadrature before, right? And so Gauss quadrature is basically a numerical technique for evaluating integrals numerically. Okay. And the benefit to Gauss quadrature is that you don't have to take any antiderivatives. You don't have to actually perform any integration. You just do a summation. Okay. Okay, so in one dimension, we had something like this, right? And so we had integral from -1 to 1 of some function f of x dx. Okay. And so what we said is that this is approximately equal to a summation of I is equal to 1 to n, okay, of some weights, wi, multiplied by the integrand evaluated at fixed values of x. Okay. And so that's the idea, right? And so, if we have, integral, we'll do one of the very famous unintegrable quantities, okay? As we do integral from -1 to 1 of e to the x squared, okay? So this is a very famous, function that can't be integrated, or at least it couldn't be when I was in college. Maybe someone figured it out now. And so we want to evaluate this with the 2-point Gauss rule. Then the way that we would integrate this would be to take the integrand, which is e to the x squared, okay? But instead of x, we're going to evaluate it at a specific Gauss point, okay? And so the first Gauss point in a 2-point rule is -1/√3 squared, okay? And then we're going to add this to e raised to the other Gauss point, which is 1/√3 squared. And the weights, for the 2-point rule are just 1. Okay, so we have a 1 out here and a 1 out here. Okay, they're kind of implied, and so I didn't write them. Okay, and so if you evaluate this in your calculator or you evaluate this in MATLAB, you can get a value. You can get an answer for this integral, without actually having to perform any integration. Okay, and so this has a lot of benefits. And so first of all, it's for integrands that are normally very difficult or very annoying to integrate. Or to find the antiderivative, this is a much faster, much more efficient option. Okay, but I would say more importantly for this class is that Gauss Quadrature kind of lends itself to a computer algorithm very easily, and so it's almost, you could almost say it was designed to become a computer algorithm. Okay. Because if there's one thing that computers are really good at, it's arithmetic, right? And so adding, multiplying, dividing, subtracting. So computers are super good at this. But beyond pre-calc, I would say computers not that good, right? Which is why we're doing finite elements, right? And so finite elements is basically just a way to solve differential equations, right? But one way that you can think of finite elements is that we're taking a differential equation type problem and we're turning it into an algebra problem that the computer can solve, because computers are great with algebra. Okay. All right, so that's Gauss Quadrature. So it's in 1D. Okay. But Gauss Quadrature can also be extended to 2D as well. Right? And in fact, that's what we're going to be using in our isoparametric approach. Okay? And so the idea is if we take a double integral, okay, the bounds have to be -1 to 1. Of some function x and y, okay, some function of x and y. What we can say is that we can turn this into a summation. Well, we'll start the summation at I is equal to 1 up until some point up there, okay? And same as the 1D case. And so this is going to be we call it a weighted sum. And so we take, our integrand here, we evaluate it at specific points. Okay, so we call it xi, yi, okay? and we sum it together, between other integrands evaluated at different points, but we multiply each evaluation by a weight. Okay. All right. And so through this, we're able to evaluate these 2D integrals without having to get into antiderivatives and such, which for two-dimensional 2D integrals can become, a lot more challenging, right? So there's a lot more 2D integrals out there that are a lot more difficult to evaluate than just 1D. Okay. Okay. So the question, of course, is, what do we choose as the Gauss points? Okay. And by Gauss points, I mean the coordinates xi and yi. Okay. And the other question is, how do we determine the weights? Okay. Right? Because if we can determine the Gauss points, we can determine the weights, then that's everything that we need to perform Gauss Quadrature. Okay. The good news for us is that Gauss Quadrature, because we're not actually performing any integration, the way that you obtain the weights and the Gauss points is by simply doing what's called, I call it like an extension of the 1D rules. Okay. Okay. All right, so I'll give you kind of the simplest case. So let's do a 1-point Gauss rule. And so in 1D, right? Okay. And so in 1D, if we did a 1-point Gauss rule, the Gauss point for that is simply 0. Okay, so it's going to be right in the middle of our integration domain. Okay, because our integration domain goes from -1 to 1, and so right in the middle of that is 0, and then we multiply that by 2. Okay, so that's the 1-point rule. You'll be happy to learn that the 1-point rule for double integrals is simply just the same thing. Okay. And so just like the 1D form, we're going to evaluate our integrand right in the middle of our domain. Okay. And so that's going to have an x value of 0 and a y value of 0. So we have f of 0, 0. And then we multiply it by 4, okay, instead of 2. Okay. Right, and so that's it, right? And so we use the same coordinates, but then we just double the weight. Okay. Why do we double the weight? Okay, and so I think that's a fair question to ask. Right? And so in the 1D case, let's look at the integration bound here. So the integration bound looks something like this, right? Our integration bound in the 1D case goes from -1 to 1, right? And so if you measure the distance between here and here, it's 2, right? So the distance between -1 and 1 is simply 2. Okay. And so if we evaluate this integral, right? And so let's say that we are working with a situation where our f of x here is just 1, okay? Right, and so we just have the integral from 1 to -1 dx, right? And so in other words, we have a constant integrand. Okay? We know that when you evaluate an integral like this, and you integrate it numerically, what you simply should get is just the length of the integration domain. Okay? And so the reason we use a weight of 2 for the 1D rule is that, if we have an integrand of 1, and so if this f of x, f of 0 goes away, then our Gauss quadrature has to preserve, the length of the domain, right? And so in the case when f of x is equal to 1, that means our integral here is equal to 2, right? And so, our Gauss quadrature should reflect that in the same way. For the double integral, our domain looks like this, right? And so we have a square. Okay. And so first we have a 1 comma minus 1, 1 comma 1, minus 1 comma 1, minus 1 comma minus 1. Okay. And the origin of the domain is right there. Right? Okay, so let's do the same exercise for this. And so if we take the double integral of a constant integrand, and so we just have dx dy, okay, so our f of x of y is equal to 1, right? What we should return from this is simply the area of the domain, right? So you take the double integral of just something blank, then you should get the area, right? And so the area of this domain, right? The side of this square is 2, the side of this square is 2, right? You do 2 times 2, that equals to 4, right? And so that's why for the 2-point Gauss rule for 2D, or for the 1-point Gauss rule for a double integral, we have a weight of 4 right there, okay? And that rule actually persists, right? And so for all 2D, for all double integrals, with the Gauss quadrature, whether you're using the 1-point rule, the 4-point rule, the 9-point rule, if you add up all the weights should add up to 4. Okay, and if you check back in your notes in the 1D for the 1D Gauss quadrature, right? I believe we went over the weights for 1-point, 2-point, and 3-point. What you'll see is that all those weights also add up to 2. Because Gauss quadrature, just by nature as being a way to evaluate integrals, it has to preserve the size of the domain in this way. Okay. And so that's the 1-point rule, and so that's fairly straightforward. And so are there any questions on this? Okay. Okay, so that's the 1-point rule, and so now let's go one step up. And so if we go one step up for the 1D Gauss quadrature, we end up with the 2D with the 2-point rule. Okay. And so the equivalent in a double integral is you can assume that we're taking the 2-point rule kind of twice, right? So we're applying it once in the x direction and once in the y direction. Okay. And so the next point up is the 4-point rule. Okay. And so this one, it looks like the following. So we have integral from -1 to -1 to 1, integral from -1 to 1 of f of x, comma y, dx dy. Okay. And so this is equal to, we're going to make 4 function evaluations, and we're going to use the locations from the 1-point from the 1D 2-point rule. All right, so it's going to be f of -1 over root 3, comma, -1 over root 3. Okay. Plus f of -1 over root 3, comma, +1 over root 3. Okay. Plus f of +1 over root 3, -1 over root 3. Plus f of 1 over root 3, comma, 1 over root 3. Okay. And so you can see here we make 4 function evaluations, and we make them for every combination of positive and negative 1 over root 3. Okay. And all of their weights are equal to 1. Okay. And so this is kind of the 2D extension of the 1D 2-point Gauss rule, right? So lots of 1s and 2s and 3s going on today. Okay. Any questions on this? Okay, so let's see it worked out in an example. Okay, so let's say that we have the following integral. And so we have integral from -1 to 1, integral from -1 to 1 of x squared y plus 3 dx dy. Okay. And we want to evaluate this integral. Okay? And so we're going to do it two ways. And so we're going to evaluate this integral normally. Right. And so we're going to use good old, 2D, good old 2D integration. And so we're going to use Fubini's theorem and all that good stuff. Okay. Okay, and then we're going to evaluate the same integral using Gauss Quadrature. Okay. And in fact, I think we use, yes, we use a 2 point, we use the 4 point. Wait a second. It is squared. Okay. Okay. And so we're going to see how close we get, or even if we match up. Okay. All right. Any questions on the setup for this problem? Pretty straightforward, right? Okay. All right. So let's do the evaluation of the integral normally first. Okay. And so the way to evaluate double integrals is to kind of go inside out, right? And so you start with the innermost one, okay? And so you kind of pretend that you're just working on this one, and you're going to pretend that the other variables are just a constant, right? And so you can see here that we're integrating on x first because we have dx here, and so we're going to pretend that y is a constant. Okay, and so we have integral from -1 to 1. Okay, so that's going to stay the same. And we're going to evaluate that integrand or integrate it with respect to x. Okay. And so we integrate the first term, and so we end up with an x cubed y divided by 3. Okay. Remember, we're treating y as a constant here, and so it's just kind of riding along with the ride. Okay. Okay, and then we're going to multiply that by we're going to add that. We're going to add 3x to that. Okay, so we have 3 integral of 3, which is a constant. It's just 3x. Okay. We're going to evaluate this between -1 and 1, dy. Okay. Okay, and so if we evaluate this, then what we get, and so you plug in 1 for x, and then you subtract the same thing, but you plug in -1 for x, and what you get is integral from -1 to 1 of 2y over 3 plus 6 dy. Okay. All right, and so now that we're at this point, we've integrated x out, so x is no longer part of the equation. And so now we can perform our integral on y. So we perform integral on y, what we get is y squared divided by 3 plus 6y evaluated from -1 to 1. Okay. Right, and so you plug in the integration bounds for that, and so you plug in 1 in for y, and then you subtract the same thing with -1 in for y, and we get 12. And so the exact solution for this integral, or the exact computation, is 12. Okay, and so there's no approximation here. And so remember, it's always important to remember that with Gauss Quadrature is not an exact method, and so you're going to end up with an approximation. And so this 12 here is kind of the gold standard. And so if Gauss Quadrature can match this, that's really good. And so that's good news for our method. Okay, and so let's go ahead and do the same thing, but with Gauss Quadrature. Okay. So integral -1 to 1 of x squared y plus 3 dx dy. Okay. So now we're going to evaluate this with Gauss Quadrature. Okay, and so this is going to be a lot more writing than it's worth, but it is good to illustrate this. Okay, and so if you scroll up here, okay, and so for the 4-point Gauss rule, we're going to evaluate it at these 4 locations, right? And so first, let's do -1 over root 3, comma -1 over root 3. Okay, and so we do that, we get parentheses. First, we have x squared, and so x squared is going to be -1 over root 3 squared multiplied by -1 over root 3 plus 3. Okay. And so this quantity right here, this is f of, write it a little bigger, f of -1 over root 3, comma, -1 over root 3. Okay. And so I plugged in x, or -1 over root 3 for x, -1 over root 3 for y. Okay. To this, we're going to add 1 over root 3 squared -1 over root 3 plus 3. Okay. And so this one here is f of, in this case, we had a +1 over root 3 for x and a -1 over root 3 for y. Okay. Then we're going to add 1 over root 3 squared, 1 over root 3 plus 3. Okay. And so this was here is when both of them are positive. So we have 1 over root 3, 1 over root 3. Okay. And finally, we're going to add a -1 over root 3 squared, +1 over root 3 plus 3. Lots of 3's. Okay. Of course, this one is f of -1 over root 3, 1 over root 3. Okay. And so that should be all of them, right? And so if you check the coordinates, then we visited basically every quadrant, right? And so we start with negative, negative, then positive, negative, positive, positive, then negative, positive. Okay, and so if you add all these up together, okay, a lot of it's actually going to cancel out, which is the part that we work the hardest for, which is all the root 3's. If you actually perform the arithmetic, it's all going to cancel out, right? And so we end up with just 3 plus 3 plus 3 plus 3, which is 12. Okay. All right, and so if we compare this to what we got above, we both got 12, and so this is great. So this shows that Gauss Quadrature is a legitimate method, and so you can use it in 2 dimensions as well. Okay. Back up here. Okay. So that's Gauss Quadrature in 2D, and so if your integration bounds are -1 to 1, then you can just basically apply the same thing. You just have to make small adjustments to the weights just to make sure they add up to 4, and you might have to evaluate your function at more locations. Okay. Okay. Any questions on this? Okay. All right. And so that's great, right? And so that's Gauss Quadrature. But we have a problem, of course, and this is the same problem that we had in 1 dimension as well. Okay. Gauss Quadrature only works when the integration bounds are -1 to 1. Okay. Right, and that same restriction occurs in 2D as well. And so if our integration bounds are not -1 to 1, or even worse, what if we're working with an arbitrary two-dimensional space? Okay. right? And so, for example, instead of this, right? And so instead of a nice, uniform triangle or uniform rectangle like this, right? What if we're working with something wonky like this? Okay. And you can't even say that those integration bounds are, something to something, right? And so it's something even worse, even weirder. And so we want to make the transition so that we can perform Gauss Quadrature, right? But to do that, we have to perform a change of variables. Right? Okay. And so we saw what this process looks like in 1D, right? And so we're basically going to be extending that to 2D. It's just that in 2D, there's a lot more that's going on. And so, I have kind of a whole set of lecture notes dedicated to that. Okay. But this idea, not only just, kind of, if we look beyond just the idea of Gauss Quadrature, to take kind of like an arbitrary shape, I mean, it's not completely arbitrary. It still has the same characteristics. Okay, and so we have an arbitrary rectangle here. And so the idea to map that arbitrary rectangle onto one that's of uniform design. That's something that we can leverage in finite elements too. Okay. And I kind of tipped my hat a little bit with that description there. Okay. And so this is of prime importance for finite elements because if you look at a mesh, right? I know it's been a while since we've looked at ANSYS, but if you remember from ANSYS, and you ask ANSYS to generate a mesh, there's no it kind of had to just make the elements just whatever size they needed to be because they need to conform to whatever geometry that you're making, right? And so performing analysis on all those differently shaped elements, is challenging, right? And so one way that we can approach this is that if we take all those arbitrary elements, but map them onto, a standard one that, looks always the same, then we can perform the analysis in kind of the same way. Okay? And so this is kind of a marriage of those two ideas, right? So the idea that, when we do finite elements, we have to do all these complicated integrals. And so it helps us to do Gauss Quadrature, right? But also the fact that just naturally speaking, just naturally when we do finite elements, we end up with a lot of elements that are very different in sizes and shapes. Okay, they all have the same characteristics, right? The same number of sides and vertices and things like that, but they're all distorted to some degree in order for it to match to the domain. Okay, and so it turns out we can solve both of those issues with the same technique, which is very rare in engineering. But that's kind of what makes this method so extraordinary. Okay, and so this idea of mapping is called isoparametric elements. Okay. And it's kind of like the coup de grace of this class, right? And so I think it's the thing that really makes modern finite elements go. And so the thing that the kind of the backbone of the fact that you can take any CAD model, load it into a software, and perform finite elements. This is kind of this technique here, or this theory is kind of the backbone of that. Okay. Okay, and so just to summarize, right? So isoparametric elements, the idea is to take an arbitrary element shape, okay, and what I call physical space, and map that to a standard, what I call parent shape. Okay. Okay. Then once we perform that mapping, then we're basically in that kind of standardized shape. Then it becomes a lot easier to do our analysis, right? So to form our element stiffness matrices, to form our element forcing vectors, right? All that becomes so much easier when we know exactly what our shape looks like. Okay. Okay. All right, and so, I just drew this picture up there, but let me draw it here again for completion, okay? And so let's say that we have, an element that looks like this, okay? And so we're gonna work with kind of the four node rectangle for a while, okay? Mostly just because it's the easiest to perform the integrals on. Okay, and so here's kind of an arbitrary element. Okay. And this is in physical space. Okay. And so when I say physical space, what I mean is kind of the exact space of the original geometry, right? And so think back to ANSYS activity 1. So I know that was a very long time ago, right? And so we had our plate with the hole, right? And so if you examine, right, if you produce like a quadrilateral mesh on that geometry, what you should have noticed was that all of the rectangles, all the quadrilaterals, they all looked a little bit different from each other, right? Especially around the hole. Okay? And so as you can imagine, right, and so you've kind of seen the process of what the software does to create the element stiffness matrices, right? If you have elements that all look a slightly different shape, performing different integrals on all those different element shapes is a nightmare, right? And so what the software does is that it says, okay, I'm not even going to try to work on this one. Okay, what I'm going to do instead is I'm going to map it onto a standard shape. Okay. So what we say that this very nice looking gentleman of a rectangle is has straight edges and 90-degree angles. Okay. And this is our standard element. Okay. And what we say, and kind of the terminology that we use, that we say that this is our standard parent element. Okay. And kind of with keeping up with the same kind of notation as we do with Gauss Quadrature, what we can say is that this standard element, the coordinates are no longer x and y. So what we have instead is epsilon and eta. Okay. Whereas the physical space one, we're working with x and y. Okay. And so this mapping that you see here, it's mapping. Mapping is always kind of a fancy term in math, right? But in essence, all we're doing is we're making a change of variables between x and y to epsilon and eta. Okay. Okay. And so this idea that before we try to do any analysis, before we try to do any integration, before we try to form any element stiffness matrix, to perform this mapping first, this is what's known as the isoparametric approach, and this is what's known as isoparametric elements. Okay? And so we're going to spend the next today, next Wednesday, and probably the Monday after that talking about this, and it is core to your final project. Okay. Okay. Any questions on this? Okay, all right, and so let's talk about the advantages of the isoparametric approach. All right, so number one, right, and so we know that when we're forming our element stiffness matrices, our shape functions are kind of forward to the entire operation, right? And so the advantage of working in the parent coordinates is that our shape functions are easy to form in those coordinates. Okay. Okay. And if you remember, when we tried to form the shape functions for a rectangle, we had a lot of restrictions back then. And even then, they still look like a mess, right? And so if we standardize even more, it's going to make it even better. Okay. Right. And so next, the next advantage is that the continuity across inter-element edges is easily verified. Okay. And so what that means is that, whenever we have finite elements, we have to have continuity of our solution, right? And so when we go from one element to the next, the solution should kind of vary smoothly in that range. Okay. And so, with the isoparametric approach, we can easily verify that we have continuity, which is good. Okay. Okay. Number 3, we already know. And so if you have isoparametric elements, you can do Gauss Quadrature very, very easily. Okay. And number 4, with the isoparametric approach, just because you're performing the mapping anyway, you can literally take almost any element and map it to the parent space, right? And so this is especially advantageous whenever you have a geometry with curved edges. Okay. So think of your final project, right? And so for your final project, you have that circular domain, right? And so when you're on the edge of that circle, you have elements that kind of curve along with the domain. Normally, that would be very, very difficult to tackle, from a finite element point of view. But if we use the isoparametric approach, then that becomes, a non-issue. It doesn't even matter anymore. Okay. All right. Any questions on this? Okay. All right. So let's talk about that mapping, because that's kind of the key to this whole operation. Okay, and so when I say that we're performing a mapping from one element to the other, we're basically saying that, if we have an arbitrary coordinate, right? And so let's say if we take an arbitrary point, okay? Let's say that we're looking at this point within the physical space. When we map it, what we're saying is that this point is going to be equivalent to another point here in the parent domain, okay? And so when I say mapping, what that basically means is that each unique point in the physical domain each unique point in the physical domain must be mapped or must have a partner point in the parent domain. Okay, and that partner point must also be unique. Okay, and vice versa. Okay, and so there's no sharing of points. And so if we say that this point here maps to that point in the parent domain, that means no other point in the physical domain can map to that point in the parent domain. Okay? So it's basically a one-to-one mapping. Okay? And in fact, that's actually the mathematical term for that. And so what we say is that the mapping is one-to-one. Okay? It's one-to-one and onto. Okay? So that's kind of the term, that's kind of the mathematical term for that. Okay. And so with that in mind, let's kind of use our same approach that we used in 1D. And so in 1D, what we did was to map certain quantities. We used the shape functions in the parent domain. Okay. Okay. And so what we can say is that our solution T, which is a function of a parent coordinates, epsilon and eta, this is equal to T1 and 1 of epsilon and eta plus T2 and 2 of epsilon and eta plus T3 and 3 of epsilon and eta plus T4 and 4 of epsilon and eta. Okay. Okay. So that's what we can do. Okay. And so you're probably wondering at this point, what are those shape functions? Okay. And so let's go ahead and write those down. Okay, and so these are the shape functions for 4-node quadrilateral. And so let me go ahead and draw it. Okay. Conveniently, it matches up with the exact domain size for our 2D Gauss quadrature. Okay. Okay. And so this point here is going to be 1, comma minus 1. This upper point is going to be 1, comma 1. This is minus 1, comma 1. And minus 1, comma minus 1. Okay. So we'll call this one node 1, node 2, node 3, and node 4 in the top left. Okay, and so our shape functions, n1 is equal to 1 over 4, 1 minus epsilon times 1 minus eta. Okay. And 2 is equal to 1 over 4, 1 plus epsilon, 1 minus eta. And 3, we have 1 over 4 times 1 plus epsilon. My mind said epsilon, but my hand said eta. Okay. Okay, and then n4, we have 1 over 4. 1 minus epsilon, 1 plus eta. Okay, so these are all our shape functions right here. All right. And so they're still quite complicated, and so these are not simple by any means, but at least there's a pattern to it. Okay, and so we can work with this. Okay. And so these shape functions are gonna form the basis of our, first of all, our coordinate transformation, but also, our element stiffness matrices and element forcing vectors as well. Okay. All right, any questions on this? Okay. Okay. And so, first of all, let's use these shape functions to perform our mapping. Okay. And so this is going to be the map between our physical and parent spaces. Okay. And so if you remember from our 1D case, what we did was we formed our function x of epsilon, right? So we said this is x1 n1 plus x2 n2, right? And so this is what we did in 1D, was we basically used our shape functions to perform our mapping between the physical space, which is x, and the parent space, which is epsilon, okay? And so we're going to do that same thing in 2D. And so in 2D, we're going to form a function x of epsilon and eta, okay? And this is going to be the mapping between them, okay? And so we have x1 n1 plus x2 n2 plus x3 n3 plus x4 n4. Okay. Right. And we have the same thing for y. And so we have y of epsilon and eta. Okay, this is going to be y1 n1 plus y2 n2 plus y3 n3 plus y4 and 4. Okay. And of course here, x1, x2, x3, x4, and y1, y2, y3, y4, those are the original coordinates of our element in the physical space. Okay. Right, and so if we had our arbitrary element like this, okay. Okay, so this is node 1, 2, 3, 4. Okay. And so this node down here will be x1, comma y1. This node here will be x2, y2. We have x3, y3, and x4, y4. Okay. Okay, so that's what those kind of represent. Okay, and so all we form now is this x of epsilon and eta and y of epsilon and eta. That's our mapping. Okay. Okay. And so again, let's kind of draw an analogy with our 1D case. Okay. And so the next step that we had to do was that once we had our coordinate transformation here, we had to take the derivative of it in order to get our Jacobian. Okay. Okay. The only difference here is that we're going to have a lot of derivatives to take because we have two functions here, right? So we have both the x and the y functions, and we have two Gauss variables as well, right? So we have both epsilon and eta. Okay? And so we're going to have to do partial x, partial epsilon. Okay. Then we have to do partial x, partial eta. We have partial y, partial epsilon, and partial y, partial eta. Okay. Okay. And so to get these, I'm just going to take our original coordinate functions here and just take the derivatives between our Gauss variables. Okay. Keeping in mind that the x1, x2, x3, x4, and y1, y2, y3, y4, those are constants, and so we don't actually take the derivatives of those. Okay. And so partial x, partial epsilon here, this is equal to x1 partial n1, x1 partial n1 partial epsilon plus x2 x2 times partial n2 partial epsilon plus x3 partial n3 partial epsilon plus x4 partial n4 partial epsilon. Okay. All right, and the same thing for this one too. Okay, so we have x1 partial n1 partial eta plus x2 partial n2 partial eta plus x3 partial n3 partial eta plus x4 partial n4 partial eta. I missed one here, so this should be eta. Sorry about that. Okay. 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 And so we're going to do the same thing with y's. Okay. And so the y's we have. Okay, so I'm just going to write them down. Okay. And finally, we have partial y, partial eta. Okay, it's a lot of writing today, I know. Okay. All right. And so these derivatives here, remember the reason we're taking them, we're not just taking them for fun, these derivatives are forming the basis of our Jacobian, okay? Okay. And if you remember when we talked about Gauss Quadrature in 1D, right? The purpose of the Jacobian has to do with the fact that, when we're performing our change of coordinates, our domain might be changing size, okay? Okay. And so we have to account for that, right? And so, if our domain is changing size, that means we have to add kind of this conversion factor. Okay. Okay. And so the same thing is occurring in 2D. And so in 2D, right? And so here is kind of our arbitrary integral in physical space. Okay. And so we're performing this on an arbitrary domain, right? And so, that domain might have an area of 4, okay, if we're lucky. But if not, it might have an area of 5. It might have an area of 55. It might have an area of 0.1, okay? And so when we make this transformation, right, so if we're eventually going to transform it into the following integral, okay? Okay. Since we're changing the bounds of this integration, we have to account for the fact that our integration domain size is going to change, okay? And in fact, in 99% of the cases, it will actually change, okay? And so to account for this in 1D, if you remember, we added this factor to the integrand. And so we added this dx d eta, okay? Or dx d epsilon, okay? So that's for the one-dimensional case. But in 2D, you can see here that we have a lot more derivatives that we have to account for, right? And so we have, partial x, partial epsilon is it accounts for the compression or elongation of the x mapped onto the epsilon. Okay, then partial x, partial eta accounts for the compression or expansion along the epsilon or along the eta direction. Okay, and so we can't just sum this up in a single factor anymore. Okay, and so what we have instead to account for all 4 of our derivatives is a Jacobian matrix instead, okay? Okay. And so J is going to be the symbol for our Jacobian, okay? And it's going to be a 2x2 matrix. And it's going to have the following values, okay? So partial x, partial epsilon, partial x, partial eta, okay? We have partial y, partial epsilon, partial y, partial eta. Okay, and so we basically take the same, all the expressions here for the derivatives, and we pop it into this matrix right here, okay? Then when we actually go to perform our coordinate transformation, what we're gonna multiply here, we can't really multiply by a matrix, because, the integral, we have to return a single number. And so what we do instead is we take the determinant of our Jacobian, okay? And so the determinant of our Jacobian is our conversion factor that we need to transform between these different coordinates, okay? Okay. And so when you're doing 2D finite element problems, one of the first things you're going to do is you're going to form your Jacobian, right? And then after you form your Jacobian, then you take its determinant, and that determinant becomes your conversion factor. Okay. And so this is kind of just a 2-dimensional analog of what we did in 1D, okay? Except now it's a bit more complicated because we're working with matrices and multiple different coordinates. Okay. But we're not done with the Jacobian just yet. And so we're still going to use it for other stuff. That's why it has a special name. If this was the only purpose was just to provide this conversion factor, we wouldn't give it such a special name. And so, we're going to use it for other stuff as well. But, we'll cross that bridge once we get there. Okay. Any questions on this so far? Okay. Okay, so it's been quite a lot of math, and so let's kind of just summarize kind of how we got here, right? And so right now we're working on the issue where we have an arbitrary element in space. Okay, this element might be arbitrarily arranged, might be arbitrarily oriented. Okay, but we want to take that element and map it onto a standard form, right? So basically one where we can perform Gauss Quadrature. Okay. And the first step that we did to do that was, first of all, we looked at our parent domain and we formed our shape functions in that domain, right? And so that's how we got n1 through n4, okay? And notice how the variables in here are epsilon and eta, which are our parent domain coordinates, okay? Then what we did was we took those shape functions and we did this, okay? And so we basically took those shape functions as a way to provide a mapping between the physical coordinates x and y to the parent coordinates epsilon and eta, okay? And so this right here, this is our physical to parent mapping, okay? Okay, and so that's how we, you know, if we have basically if we have parent coordinates epsilon and eta, we can use that to compute the physical coordinates x and y, you know, for this element. Okay. Then what we did was we took those functions, we took those mappings, we took their derivatives. Okay. Right, and so those derivatives kind of express, you know, how different those mappings are, and then once we had those derivatives, we put them inside this Jacobian matrix to form kind of our transformation, okay? And so you can see this and so one way to view this Jacobian matrix is that this is kind of the key between relating things in the physical domain versus the parent domain, okay? Okay, so let's go ahead and continue. Okay. And so one other thing that we can do with the Jacobian is we can take its inverse. Okay? And so we'll call this J minus 1, okay? And this is basically going to be, you know, all of the derivatives in there flipped on its head, okay? And so this is going to be partial epsilon, partial x. Okay, this is going to be partial eta, partial x. Okay, it's going to be partial epsilon, partial y, partial eta, partial y. Okay. Okay, and so why would we do this, right? So why would we take the Jacobian and take its inverse? Well, you know, let's take a step back. Okay, and so if you recall from last time, you know, when we form our element stiffness matrices for 2D elements, you know, we end up having to evaluate something like this. Okay, and so this is from the weak form. And so we had double integral of the gradient of W multiplied by K multiplied by the gradient of T dA. Okay. So that was from the weak form of our equations, right? Where gradient of W here, right? When we put this in vector form, look like the following. And so we had W1 W1, W2, W3, W4, okay? And this is multiplied by partial N1, partial X, partial N2, partial X, partial N3, partial X, partial N4, partial X, okay? Partial N1, partial Y, partial N1, partial Y, actually partial N2, partial Y, okay. Partial N3, partial Y, partial N4, partial Y, okay. Okay, and so, and we have a very similar expression for the gradient of T as well, okay. All right, so I'm not going to write down the gradient of T again, okay. But what I wanted to highlight here is that, you know, when we did this for the triangle, or I guess in this case it's for the quadrilateral, right? All of these shape function derivatives are performed with respect to X and Y, right? In other words, we can say that all the shape function derivatives are performed with respect to the physical coordinates. Okay. And so that's fine to do, okay? And so you can do this just fine. But the requirement for that is you have to have the shape functions themselves also expressed in the physical coordinates, okay? Okay. In other words, we have to have n1 of x and y, and 2 of x and y, and so on and so forth. Okay. Okay. That's a requirement in order for us to take those shape function derivatives, right? Is we need to have, in order to take the derivative with respect to x, we need to have x show up in that function to some degree. Okay. The problem is, if we're using isoparametric elements, we don't have that, right? And so if we scroll up here, we look at what our shape functions look like. Okay. Our shape functions don't have x and y; they only have epsilon and eta, right? And so when we try to take these derivatives, we actually can't do them because we don't have them in our shape functions. Okay? Okay. And so we have a mismatch here. And so this is a different issue entirely. And so, this goes beyond just, change of coordinates for Gauss quadrature. We need to make a change of coordinates for the derivatives themselves. Okay. And so what we need to do is we need to express these physical shape function derivatives in terms of parent shape function derivatives. Okay. Okay. And so this is where the Jacobian inverse is going to come into play. Okay. And so let me give you a couple examples, right? And so let's take partial n1, partial x. Okay. So that's just one derivative up here. Okay. But I think just by doing one, you kind of see where this is going to go. Okay. Okay. So partial n1, partial x. One way that we can express this is that, right? We can express this as partial n1 partial epsilon, okay? But we have to convert that epsilon to x, right? And so we're going to multiply this by partial epsilon partial x, okay? And so, it's not algebra, it's calculus, but what you can say is that these factors of partial epsilon on both the denominator and the numerator are going to cancel out, okay? But we also have contributions from eta too. So we can say partial n1 partial eta multiplied by partial eta partial x. Okay. And same thing for y as well. Okay, so just to give you one more example. Okay. Okay. the thought that I'll leave you with, before we wrap up for the week, is let's look at these factors right here. Okay. These are the factors that we need to basically convert between a physical shape function derivative and a parent shape function derivative. Okay. Look what has these guys. Right? Conveniently, these guys are expressed also in our Jacobian inverse. Okay. And so what we'll see next week on Monday is that we can use the Jacobian inverse to basically form an expression for this guy in terms of the number one, the shape function derivatives in the parent coordinates, as well as the Jacobian inverse. Okay, and so we're going to get around this problem of performing derivatives in the physical space by utilizing that Jacobian inverse. Okay. All right. Any final questions on this before we wrap it up for today? Okay, all right, and so that's it for today. And so, we made some good progress. And so I think hopefully on Monday, we'll be able to see the isoparametric algorithm that you guys can apply for your projects. Okay. All right, so thank you everyone for tuning in today. It's another heavy math day, I know, but that's kind of just how this is. Okay. And so if you have any questions, on the homeworks or before the midterms, please let me know. And we can either chat over email or we can have a Zoom call. Okay. And so best of luck studying. Have a great weekend, and I'll see you guys next week. Yep.
I still really don't understand how close to change there.
All right. Let me come over. So I think probably the best way is to right. Yeah, so all these can actually got. And so if we go back to our shape function here, these ones, you can take the derivative of these, and fill in. And so I guess the other thing to recognize is that for this particular problem, you can say that x1 is 0, x2 is 1, y1 is 0, and y2 is 5. And so that's and that goes for all papers. So it's a square domain. So x1 and x4 are the same. Y1 and y2. And so what is your y1?
I thought it was y1, y3 is the same as y2.
Yeah, it's if you go by that, y1, y2 is the same for y2. Because we go back. So those are going to be the same as the other, right? So because you draw this domain. Yes. Oh, sorry. Yeah. Okay. So then.
So is it like this? Is it the odds matchup and the evens matchup?
Yeah. So I mean, there's two that are the same. So y1, we'll say y1, y2 the same. So we'll say that's 0, right? And y3, y4 is 6. That's going to be 1. Because if you draw this domain, then your origin is going to be right here, 0, 1, 0. This is the bottom left. The bottom right here we have 10, comma 0. And the top right we have 10, comma 5. And the top left we have 0, comma. And so those are the four. X1, y1, this, x1, y1. what we can say here for x2, y2, and then for the other one, so we picked up the top right. We said that x3 is 10, or y3 is 5. This point right here is 5. That one is 10 colors. Exactly. So this is x1, y1 right here. This is x2, y2, x3, y3, x4. Yep.
So then I end up with basically that's with respect to what I think the function here. So negative 1/4.
Yep. That's that one's absolutely.
So then I take the derivative with respect to a dash.
Yep, minus 1/4 of this one. So this turns into 6. Let me change that because I actually was hoping to get to this word today, but we didn't get as far as I wanted. So let me change this one. So instead of a 4-point rule, let me change it to. Let me just make that one shorter because it's we didn't really fully do that example. Let me make
We'll probably want to go on so that's a good one.
okay.
Yeah.
Yeah. Just do A through C and then we'll worry about these later because I think we didn't really get we need to you kind of need to do that now. Just know what to do. Let's do D then. Okay. So I do kind of have one more assignment after this. Just because there's some of this stuff again. And there's the programming problem from the last time programming. I heard there was that problem. I didn't want to ask about this one because I didn't want to specify that before the exam. But then I do want you to do that one before the project. It's good practice.
I probably, if we have to do the I probably won't even ask you about that tomorrow.
Yeah, I'll send an email about that.
If I have problems with 3, I'll ask you.
Okay, yeah, that one you can follow the
Yeah.
yeah, exactly.
Okay, sounds good.
Yes, sir, questions? What's up? Yeah.
I can measure this little line and then just yeah, but
Yeah. Yeah, so the key to that is to form these two matrices. So these two matrices are simple to do, they don't involve all this sort of thing. And so you have partial, basically the partial derivative of all the shape functions, and they're repeating. So you have the same 6 here, the same 6, which is triangles. And so the way to do this is to basically compute the shape function derivatives. And they have these values. So enter these into math. You have 6 values. Put them into a 3 by 2 matrix like this. and then put them into a different matrix based on
It looks
and then
flush.
just multiply
It's impossible.
without having to do all.
It's literally not a picture, it looks flush.
Because you have one radius there that's.
Yeah, bro, there's no space.
It has to be space.
So the K's, so if the K is
I
constant.
mean, I'll ask, I'll put the whole thing
So
together.
after you perform those two matrix
Ask you
multiplication,
that, yo,
and you just multiply by K.
And that other.
And you multiply by
I told you about,
You
there's
just
no way
multiply
to get
The 1.5.
constant.
It's 25.
Yeah.
You could be off by half.
There's no way to get which dimension.
Exactly. Okay, don't worry about the W's. Because we don't really concern ourselves with that. Okay, just after you perform the matrix multiplication, just multiply the result by K. Whenever we started strong forms. So I don't remember. So I think we took the first midterm on week 7. So it's probably around that. And so until week 12 was last week. Yep. Yep. Yeah. No. So for this one, you basically have these two integration vectors, right? So we have 0 and 10. And so if you consider this to be x1, so 0 is x1. And then 10 is your x2. Then you have to find the function of x of epsilon. X of epsilon or x of epsilon. Sorry. It's just I'll think about it. So it's just one, right? So it's just x of epsilon. X1 times n1 plus x2 n2. Okay, so n1 n2 those are your shape vectors. So you're going to plug in for those ones. And then what you have to do then is you're going to take this. So this is going to be a function of epsilon. And so you're going to plug this in everywhere that you see x. You're going to plug in. And then in addition to that, you have to multiply by the additional factor up here, which is the Jacobian. So you take the derivative of this with respect to epsilon and then plug that in at the end. So we did an example. So if you look at the end of the notes of the finite element, I think the finite element notes, I think it's at the end of those ones. So it kind of walks through this. So you just kind of follow this. Yeah, and I forgot on this homework. So problem 2D is a 2D Gauss Quadrature with arbitrary bounds. And so I think I'm gonna make that one functional for now because we didn't get to finish it. So 2D you don't have to do, but A, B, and C you should do. No, yeah, it is a fair amount of arithmetic, but it's just follow the example in class and it should be done. Yep. Questions?
Yeah, go ahead.
Oh, okay. Okay. And so the Neumann boundary condition, remember that's if you draw the weak point, right? It's kind of that extra term.
Here's like,
And so the way that I see it is that if you look at the weak point quantity, when we evaluated the Neumann boundary condition, there's no interval, which is a better look at that. But if you look at the weak form of 2D, then everywhere in the 2D weak form we have double intervals. But for the Neumann boundary condition, we have
so these two.
one unit, again, there's one dimension. It's a minor. So these ones are double intervals. And so in 3D, you're going to follow the same logic. These intervals here will be triple intervals because it's 3 dimensional space. Yeah, that's going to be a. So that's And so what I was getting at with that problem is that if you're going with boundary condition, the integral should be one dimension less than whatever you're doing. And that's always the indicator. And when you do your project, part 3 of the project,
So that's what
you'll see it. So you're gonna fill it up basically at one.
nothing is going to.
Okay, yeah, that's fine.
It's something like this. This one, all those people, they share with, they create a culture, that exists. But only of this goes to that.
Yep. Yeah, that's perfect.
No, no,
Yeah, and then part D, I was telling Jacob, I was telling him that part D of problem 2, we didn't get to it. I actually forgot that I assigned it. And so we obviously didn't finish doing that here, and so I'm gonna make that option. So I'm gonna send an email right now. It's just, in order to do this, you have to do the changes there. And we didn't get to finish that. So I'll make that one optional for them. All right, yeah, you're not gonna do that on the exam. I mean, that's way too much work to do on the exam. Anyway. But it is good to know for the. So I'll just make it optional.
Okay, so
I haven't decided. I haven't wrote the exam yet.
all right.
But usually for this exam,
Just give me till 9 o'clock.
actually I won't say. That's saying too much. You're missing it too. Be ready for it.
That's it.
Yeah.
Thanks.
You have a question?
Yes.
Okay.